Good evening, everyone. Thank you for joining us at the event and making it a memorable celebration. Myself, Pritili Modak. I am a trainer of Modak Academy, a platform driven by vision and value. Today we are presenting Gravity, the final frontier presented by Professor Sumanta Chakraborty. Professor Chakraborty is an assistant professor, School of Physical Science, Indian Association for the Cultivation of Science, Kolkata. Currently, he is an associate editor of the renowned Internal General Relativity and Gravitation, published monthly by Springer. He has received Young Scientist Award from the Joint Initiative of the Department of Science and Technology of the Government of West Bengal and the Central Kolkata Youth Organization. Also, he received NRC Young Researcher Award from IAGRG. Not only that, Professor Sumanta Chakraborty received Mobility Grant from Max Planck Society. His paper on black hole shadow has been published as Rapid Communication in Physical Review D. His PhD, this thesis has been published by Springer in its Springer, this series. An article is written by him and has been selected as editor's choice in the journal General Relativity and Gravitation. He received V.V. Narlikar Best Thesis Award from IAGRG. He received honorable mention for his doctoral research by the Italian Gravitational Physics Society. Now, without any further delay, we will turn the time over to Professor Sumanta Chakraborty. Sir, please start the deliberation. Thank you.
Thank you very much for your very nice introduction. And I will start my presentation now, but I guess there is some other thing which is going on around us, namely the lunar eclipse. And after the lecture, I guess all of you can enjoy it by going outside your room and looking up at the sky. And this talk will also be things that you can see by looking at the sky. I will explain what see means. So I will start by presenting what I want to show you guys and share with you. So I guess all of you can see my screen properly. So just a brief comment about the research institute that I am from, namely Indian Association for the Cultivation of Science. So it is the oldest research institute in India, which will celebrate its 150 years in the next year, 2026. IACS, in short, is also home to two of the most important physicists in our country. First is Professor C.V. Raman. You must have heard about them, all of you, because he was the only physicist of India who got Nobel Prize in Physics. And Professor C.V. Raman did his work exactly at this institution, IACS, and the instrument with which he first measured the Raman effect, for which he got the Nobel Prize, is still there at our institute. The second person is someone whom you may or may not know, but he is from this part of the country. His name is Omon Kumar Raichaudhuri. So he derived an equation which goes by the name of Raichaudhuri's equation for obvious reason. And it is said that after Einstein's equation, which is one of the most important equations in the history of physics, the Raichaudhuri equation is the second to it. So therefore, it seems two of the most stalwart people in physics in India have worked and produced their papers from the very institution that I am in. So it's a really proud moment to share with all of you. Now, the way I have structured this lecture is that there would be some topics of broad general interest. There would be some nice videos and presentation which will show you how people actually progress gradually in doing physics. and how astonishing the world around us is. So the starting point of any discussion is related to this cube of physics. So as we know that there are three fundamental constants in our nature. One corresponds to the Newton's constant, which is sitting over here, capital G. One is the Planck's constant, which is related to h bar. The other one is the speed of light, whose inverse is what I have represented. Now, when we learn class 7, 8 physics course or physical science course, there we typically learn about the Newton's laws of motion. Namely, force is proportional to acceleration, the second law of Newton. That is what constitutes the basics of classical mechanics. For that, we need neither Newton's constant, neither the speed of light, nor the Planck's constant h bar. Now, if you go for slightly higher classes, then you realize that Newton also provided a law of gravitation between two massive objects. And this is something we call as Newtonian gravity. In short, it says that if you have two massive objects, the force between them is proportional to the inverse square of the distance. And this proportionality factor is given by this Newton's constant G. So by the time you gave your class 10th exam, you have learned about Newtonian gravity to some extent and classical mechanics also to some extent. When you go to 10 plus 2, that is at the level of 12 classes, then you started realizing that classical mechanics is not really correct. And there are some non-trivial corrections which happens if you move at a very high speed. And these corrections are called special relativity. Similarly, you also start to realize that when you go to very small length scale, which of course you cannot probe in your everyday physics, you start seeing a very different phenomenon. And these are collectively called the quantum mechanical effects. Which are present. But when you go to bachelor's level, you understand them and master them. So you have a very good understanding of special relativity as well as the quantum mechanics. So you see, as you progress in your physics discussion, you learn about various vertices of this cube. First, classical mechanics, Newtonian theory in the school level, special relativity and quantum mechanics at the bachelor level. And if you go ahead and master in the physics courses, that is master's course in physics, you will learn about general relativity, where G and C both merge together and will be the primary discussion for us today, as well as quantum field theory, which involves H bar and C. Now, there are two other vertices that you can see. One corresponds to this theory of everything, where G, C, and H bar are all present. And the other one corresponds to non-relativistic quantum gravity, where G and H bar are present. These two branches or these two vertices of this cube, no one knows about what is going to happen to them. We have no understanding what is the theory of everything, and we have no understanding about any features of quantum gravity. And this is the biggest puzzle of today's physics, that how can we prove what is happening at those two vertices. So you see, the physics as it stands today, you can learn almost everything by the time you finish your masters. And the next things what you do are all about quests to learn the other vertex of this cube, namely the theory of everything, where gravity and quantum theory mixes with each other, leading to an unknown theory. And what are their experimental predictions? There have been lot of progress on the direction from quantum field theory. People have done lot of calculation on that, and we have a very nice standard model of particle physics. While when you move from general relativity towards the theory of everything, that line is not very well understood. And that is what we are going to discuss today, and that is why gravity is the final answer. Now let me go back to the forces around us. So there are four forces with which everything in the universe can be explained. And these are electromagnetism. So this is why you can hear my lecture. There is Wi-Fi in your room, and also there is a laptop with which you can see the screen. Everything is primarily due to electromagnetism. Then, of course, we exist because the air exists around us, and the air exists because Earth has the gravitational pull. Similarly, Earth moves around the sun again due to gravity. So, therefore, gravity is also something that is surrounding us. What about the weak force? Maybe some of you, or maybe all of you, have heard about this Chernobyl disaster. If not, you should look it up. There is actually a very nice web series about the Chernobyl, and that is something worth looking for. Anyway, so the Chernobyl disaster effectively means you must have heard about nuclear reactors from which power can be generated, and people say it's much more cleaner than the other sources of energy in our country or surrounding. Now, the force due to which this energy can be generated in nuclear reactor is due to this weak force. So, Chernobyl disaster is due to the weak force. And the last force is called the strong force. So, strong force is the one that keeps everything together in the sense that we are all made out of electrons, protons, neutrons. That stability of proton, because we know protons don't decay, is due to this strong force which exists. So you see, all these four forces are extremely crucial for our own existence. If you switch off any one of them, or if you tweak any one of them, we would not exist. For example, in the Newton's gravity, we all learned that there is a inverse square law force. But if you make it inverse cubic, then we will see that there is nothing. I mean, humans cannot exist. Orbits would have been very different, and the whole universe is going to be very different. So, a very small change, 1 by r square to 1 by r cube, changes the physics in a very drastic way. Now, the weakest force among all of this is gravity, and that is why it has been elusive. So, I will give you an example. Let us suppose all of us has gone to various beaches, for example, maybe Puri or maybe Andaman and so on and so forth. For some beaches, the tides are not very strong. Like the high tide and low tide, there is not much of a difference. And that's the case say, when we have a weak tide, say for example. And suppose with the information or experience that you have with this weak tide, suppose you go to another beach where the tide is actually very strong, nothing will match your experience. The same is true for gravity. We know how gravity behaves in the weakest form, like in the solar system, but we do not know, we have no idea how it behaves when it becomes strongest. And where does it become strong? It becomes strong for the black holes. And what are these black holes? So black holes are effectively some compact objects from which nothing can escape, not even light. I will come back to more details about this formation of this black hole in a few slides. And the main topic of our discussion will be understanding these black holes through these two new observational tools that have emerged, namely the black hole shadow and gravitational waves. Okay. Now let us move to two most fundamental principles in physics. So this slide can be biased because it is my own perception, that's what it carries. So, but I think mostly people will agree with me. The point why people do physics is precisely because of the fact is that people want order in the system. In the sense, suppose the law with which you describe the motion of moon around Earth is very different from the principle which describes motion of Earth around Sun. Then the physics would have been extremely complicated. You have to remember, oh, I am discussing moon, so I must be doing this kind of a way to treat the problem. Oh no, I am studying Earth moving around sun, so I must be treating the problem in a different way. So that will make our life very complicated, and it's not something that is something we desire. So physics tries to concise everything. So effectively, all the four forces that exist in our universe, at least to some extent, can be represented by a single quantity, which is called the action. If you guys have seen the very famous movie, which is called The Lord of the Rings, you will realize that they have a very famous line as well, which says, one ring to rule them all. Here also, the motto of physics is there should be a minimal number of principles to explain all the physics that's happening around us. Everything that happens can be explained by using a very minimal set of principles. And these two principles, which I have stated, is actually the two most fundamental principles of physics. There is something called an action principle in physics from which you can get anything that you want. For example, if you throw an apple up, it will come down. That also comes from the action. The earth, which is moving around the sun, that also comes from the action. How an electron moves inside an atom, that should also come from such an action. That is the idea of doing physics. And the second is, of course, something that seems very obvious is that if you have a symmetry, then there must be some conserved quantity. So I will not go into more details with this physics oriented and maths oriented discussion because of the audience. So I will just jump into some history and then I will go over to what we do now in the context of gravity. So the father of modern science is named after Galileo because Galileo is the one who did a lot. I mean, actually, the physics, the basic ideas of physics came from him only. So the ideas like velocity, acceleration are all due to Galileo. Then the relativity principle on which everything is based on, what it means is that whether you see, I mean, the audience sees something or I see some physical phenomena, it is going to be identical. There would not be any difference between them. Modules or some other subtleties, but all over, this is how it sounds. Then Galileo also made a very distinctive claim, and this is something I'm going to show you a proof of this claim in a moment. So what he said is that when you define the second law of Newton, there is a notion of a mass because force is mass times acceleration. That mass is referred to as the inertial mass, and when the mass sinks into the gravitational force, F equal to gmm by r square, that is called gravitational mass. Now, typically, people assume them to be same, and Galileo is the first one to prove that these two masses must be equivalent. So I will show you experimental verification of the same in a moment. Galileo also has a lot of expertise in the discovery of telescope. He is the one who first studied the sunspots, which is related to the solar storms in the sky. He also find out phases of Venus, various satellites of Jupiter, and rings of Saturn through the telescopes that he developed. So I must say that he is not the first one to discover telescope, but he is the one who gave telescope one of its modern form. Now, if some of you have plans to visit Italy or if you live in Italy, then there are a few places which you can actually do. For example, in Padova, the place where Galileo lived, he was there for a long time. You can see a plate saying that Galileo lived there. Similarly, Galileo was born in Pisa. So if you go to Pisa, the Leaning Tower of Pisa, you will see Galileo's home over there. And Galileo died in Florence. So if you ever go to Florence, there is actually a villa in the outskirts of the Florence, and where Galileo spent his last few months. And you can also go and see that. And in fact, there are some a museum in Florence where Galileo's portraits are actually present. And I think this one could be from there. Anyway, so let me come back to the equivalence of inertial and gravitational mass. It says that suppose you drop a feather and a hammer from equal height, like a feather and a hammer from equal height, it will reach the ground at the same time. Now, this might seem very impossible to you because the feather is definitely going to take a lot more time than the hammer. But the reason is air resistance. If you could do this experiment in a room without any air, then you would see that they would land at the same time. But the next thing is not about any room, but an experiment that some Apollo astronaut carried out on the moon with a hammer and a feather. I will just run this video and then I will come back to it after it finishes. One hand and hammer on the other, and both actually reached the surface of the moon at the same time, proving the equivalence of the inertial and gravitational mass, something that Galileo predicted long before any man landed on the moon. Okay, I will now come back to the next important figure in the history of physics, namely Isaac Newton. And Isaac Newton sort of uses to call himself a natural philosopher. So Isaac Newton had contribution to various branches of physics as well as in mathematics. And people think that he had some thing to do with the invention of calculus, but there are fierce debates about it because generally the credit goes to someone else. But keeping aside those debates, one
That's
thing
your hand.
is any question?
No, please continue. Please
Oh,
continue.
thanks. Yeah. So, modulo those debates, what Newton did is something phenomenal. He actually the first one where he involved calculus into physics calculation. And that is why, using those ideas, we could actually show that if you have inverse square law for gravitation, you can actually get Kepler's law. What it says is that the time period that it takes for Earth to move around that sun, or for that matter, any planet around sun, If you take the square of that time period, that should be proportional to cube of the radius. So these are something which is extraordinary that Isaac Newton derived, and he also gave quite a nice ideas about tides as well. And as I said, he is the inventor of the modern form of classical mechanics, and you all know about the Newton's laws of motion starting from our school days. He also had enormous contribution in optics, while Galileo built something, a telescope which is called refracting. Newton built a telescope which is reflecting. I mean, a schematic diagram is below here. So you can see it falls due to reflection out of this small mirror tip here. And actually today, most of the giant telescopes are reflecting telescopes because of the very good resolution that you can achieve with it. And Newton is the first one who provided us a notion of color dispersion in a scientific manner. So after that, I will move on to Albert Einstein. And we all know him as the E equal to mc squared. So Einstein did some remarkable things in the sense he proved Newton to be wrong. He discovered special and general relativity. He founded basics of quantum physics like photoelectric effect. He worked on Brownian motion, which is a very important field in statistical physics, which is often ignored. And most importantly, he predicted the existence of gravitational waves in 1915 and which was discovered in 2015, and we are celebrating 10 years of its discovery in the next month. So I would like to share an historic anecdote about Einstein here, just to show you that no one is perfect and everybody made mistakes. So you see, when Einstein first wrote the paper on gravitational waves, he said that gravitational waves do not exist. That was his conclusion. And he sent it to Physical Review, which is a well-known scientific journal, for publication. But Physical Review has a policy that every paper, scientific paper that is sent to it, must go through a recurring process. That is, someone would read the paper, would see if it makes sense, and then argue or say that it is not acceptable or things like that. Now, the referee in this case noticed errors in Einstein's paper, and he said that, look, I think there is some mistake, and if you correct them, it seems gravitational waves do exist. Now, Einstein was extremely unhappy that, okay, I am a so much world famous man. He was very famous by 1915 itself. How come you review my paper? I mean, this cannot just happen. So he withdrew the paper from the journal and then he submitted it to a German journal. But with the conclusion now changed to gravitational waves do exist. So therefore you see that he was initially wrong and that he realized and he corrected it. And had he predicted that no gravitational waves exist in 1915, I did not know. I mean, if people were at all concerned about gravitational waves and try to see them and so on. So it was a monumental mistake and its correction, which is something that we have seen after 100 years. Okay. Now, what made Einstein so famous? So in the right hand side, you can see the cutout from the Times magazine in New York, which is considered to be the most influential magazine. And it says that lights all askew in the heavens. It means that lights bend. Light do not travel in straight lines. So Einstein theory triumphs, stars not where they seemed or were calculated to be. So anyway, so the idea is very simple. So here is the sun, it is present here. And here is the art. Of course, this is not up to the scale, but just for an illustration purpose. And suppose there is a star which is present here. Typically, you would see the star coming through the sun. Now, that is not possible because you cannot see anything beyond the sun. So, therefore, normally you do not see the star. But the starlight does not follow a straight line in the gravitational field. It actually bends, as you can see, the blue one, and then it does recharge, and therefore it will appear to us as if the star is blue, while the star is at this place. Now you will ask that, okay, all these things might be true, but how can I see a star which is beyond the sun? I mean, it should be very close to the sun. And I know that sun is very luminous, so there is no way we can see those tiny stars over there. Now the reason we can see this is because of eclipse. Because when you have a total solar eclipse, the sun is completely blocked by the moon, and therefore you can actually see the night sky and you can see the stars. So this is precisely the effect that Eddington used, that is the solar eclipse, in 1919 to measure this observation. So Einstein predicted that this bending, which is the angle between this blue line and the white line, should be larger than the Newtonian prediction by a factor of 2, and Eddington indeed saw that the effect is larger than Newtonian by the factor of 2. So everybody was very happy and triumphed, but I will tell you another story regarding this. So the point is, Einstein first gave this prediction in 1940. And actually, he predicted that I get back Newton's later, there is no factor of 2 initially. And then, after about 6, 7 months, Einstein rechecked his calculation and said, no, I made a mistake, there should be a 2. But you see, what happened in between is that between that 6, 7 months, there was a solar eclipse. And some German scientists was ready to measure this bending angle during that eclipse. And you realize that if that scientist had been able to measure the bending angle, then Einstein would have proven wrong actually, because the bending angle is larger than Newtonian, and Einstein had said, oh, my theory matches with Newtonian, which is not the case. But fortunately, I mean, not of course, it's unfortunate that at that time the World War One broke out, 1914, and therefore all those expeditions were cancelled. The observation was possible only after the World War has ended, and that's in 1990. So you see, everyone make mistakes, but with a bit of luck and with a bit of courage, and the fact that you should go and recheck what you have done before, put Einstein to the place where he is now. Like everybody knows it. Okay. So we have told you about all the main people, Galileo, Newton, Einstein. On shoulders of them, theories of gravity exists. Now comes, okay, so you have understand the history. Now what is the physics? How does everything become? How are we present here, and so on and so forth? So this is how it all began. Yes, questions? Okay. Probably not.
No, sir, please.
Thanks. Yeah. Yeah. Okay. So you see here, this is a typical history of our universe, or what is believed to be the history of our universe. So we start with an initial epoch where quantum effects are present and no one really knows what happens there. And after that, there is a phase where universe expands in an exponential manner. That is called the inflation. And at that time, all these stars were being made. Like photon was already there, but there were no electron, no proton, nothing was present. And they started to be formed here during a regime which is called Big Bang nucleosynthesis. So proton, hydrogen, these things could form. And that is something which we see here at the afterglow light, it is mentioned. This is called cosmic microwave background radiation. If one has a microwave antenna, then they can actually see a little hum coming from a distant universe, which is due to this particular afterglow which is present. People have measured it. Then there were dark ages where there were not many things which are happening, and after which stars starts to form. So it produces a lot of gas, they gradually collapse under their own gravity, and then the first stars are forming. And after that, things progress, stars die, planets are formed, galaxies are formed, and so on and so forth. And this is how the universe looks like today. So here I will not talk about more about this dark energy or accelerated expansion because that is some other puzzle which will take a lot of time. But rather I will mostly concentrate myself on the star. So what is a star made out of and how is a star stable? So typically a star is at the beginning when it has just started is made out of hydrogen and helium. So the hydrogen remains at the outside and the helium remains at the core. Why? Because hydrogen fuse with each other. So two hydrogen joins to form helium, and that's how it generates energy inside star. And that is precisely the way sun is also generating its energy by converting hydrogens to helium. Very good. Yes. So now hydrogen to helium is going on. Now you see a star does not have an infinite fuel. Like a car, even if you fill it with petrol or diesel, or maybe an electric vehicle which we are fully charged, after you move for a certain distance, the charge is going to come down, the amount of petrol is going to come down, so you have to recharge. But for stars, recharging is not an option because there is nothing with which it can be recharged. So therefore, the amount of hydrogen starts to deplete. Then what happens is that the helium starts to fuse and it forms heavier and heavier elements. Like it forms carbon, it forms oxygen, it forms neon, it forms magnesium, it forms silicon, and it also forms iron. So you see, carbon, which is one of the main ingredients for organic life forms like us, actually comes from a star because it's the star which through nuclear fusion creates this carbon. Now what happens is that when you see an old star like what our sun would be after maybe a few thousand billion years, then you will see that at its core there will only be iron, nothing else. Then there would be silica, so it would be like a onion-like structure with hydrogen at the top. Now the problem is iron molecules do not fuse, which is a very interesting property of iron and it's related to the extreme stability of iron molecules. So that means I have a star which starts to contract gravitationally, but there is an internal radiation and which is causing pressure to moving outwards. The star is stable. There is a force inside, gravitation. There is radiation outside, so star remains empty. But as soon as the nuclear fusion stops inside the star, the gravitational force starts to dominate and the star actually contracts. So what happens is that there are two pathways. One, so is the birth of a star from what is called a stellar nebula, stellar gas cloud, and things like that. So one could be star of the size of a sun, or other could be very massive star. Then, as it dies, which is when the iron forms at the core, it becomes a red giant. And the sun, for example, its radius will be so large that I think it will be of the order of the Mars. So that means we will go inside the sun. Then what happens, as I said, the gravitational pull dominates and there is a huge explosion. Boom. And in that explosion, everything falls surrounding to each other. Like you can see this glow, which comes from material which has come out of this collapse. And there is a small central object which is called the white dwarf. And this happens if the mass of the star is smaller than 1.4 times the mass of the sun. And this bound is also incidentally derived by an Indian astrophysicist named Subramaniam Chandrasekhar, and that's why this bound is called Chandrasekhar bound. If it is a massive star, it also dies, but it becomes a very large one, which is called red supergiant. And then there is a supernova, which is an extremely bright phenomena. And actually, if it exists or if it happens close by, you can see it in the day sky also. It is so bright. And the end states can be two. One is a black hole and the other is a neutron star. Nothing comes out of a black hole. Neutron star is a very, very compact star, but still it emits electromagnetic radiation. So with that finished, I'll skip this slide. Let us go and discuss about the nature and physics of black holes. So it will be short. I will show you some videos and mostly that's it. I will just give you a broad idea. So this is a typical picture of a black hole where inside we have an enormous gravitational pull so that nothing comes out, even light. So that's why it looks black because nothing comes out of it. Outside of a black hole, typically there would be what is called an accretion disk because there would be a star. Typically, all the things appear in companions. So there are two stars which are moving around each other. One of them has turned into a black hole, say for example, other still remains. Because of the massive pull, matter starts to flow from one star to the other, and that forms this accretion field. The color determines the temperature. It is colder outside, but as matter tries to fall in, the temperature increases, and it is highest in the white color region. And what we are interested in is when two such black holes come close to each other. What happens? That is a question that one asks because black holes have the highest gravity. So if two black holes come closer, something violent must be happening, and we must see some signature of. And these are some pictorial depiction of how you can detect such black holes through bending of light and things like that. But we will not focus much time there. This is a very important picture because it shows you how eyes can be deceiving. Because through eyes you only see a very little spectrum, while typically the spectrum is extremely broad. So the electromagnetic wave is what I am discussing, nothing more. So there is radio. With radio, you see that there is nothing at the center. It seems a black region, and the most of the glow comes from this region only. Now you go to infrared, you start seeing some very bright region at the center, and then you see that there are a lot more material outside than you can see in your video. Then you go to visible, you see the central region, which is very bright now, but you may not see all these structures, the full extent of this spiraling structure here. Is the visible. Then you go to ultraviolet, where you see the center very clearly and very brightly. And ultimately, when you go to X-ray, you see nothing else but the center. So that means, if you see in only one wavelength, which is that of our visible light, which is 400 to 700 nanometer, you see only a part of the story. To know the full story, you have to scan through all the frequency ranges, and each of them is going to tell you a different story. Based on that, people were trying to look for the other class, which is the black holes. So this is how a gravitational wave emitted from a black hole looks like. So we have two compact objects which are moving around each other, and as a consequence, it is generating ripples in the space time. This is just like when you throw something into the pond, then there are ripples on the surface of the pond. So similarly, these are the ripples of the space time. And they are every present. You may think that they are only can be seen, they are only exist for black holes. That is not true. I am waving my hand, I am generating gravitational wave. You are nodding your head, you are generating gravitational wave. A tree is weaving in wind, it is generating gravitational wave. The earth is moving around sun, it is generating gravitational wave. So effectively, everything which is in motion generates gravitational wave. Why we don't see it? Because it is extremely, extremely small. For example, even in this case, when you have black holes, do you know what is the measurement length scale of gravitational wave? It is 10 to the power minus 21 meter. That means you have to measure a distance which is of order 10 to the minus 21 meter, which might sound impossible, and actually people thought it was impossible for a long time, but it seems it is not. So I will show you a pictorial depiction of how this merger of black hole actually works. So this shows that two black holes are actually the black blobs here are actually moving around each other, and there is this high deep potential well between them, and they are gradually moving around each other. You see, initially they were spherical, but now it seems that they are probably slightly distorted due to the high gravitational pull of the other. And they are coming closer and closer to each other because they are radiating out gravitational energy. And at some point, they actually merge. Like here, the two potential wells join each other, and these two black holes also join. You see, the two black holes are now only one single object, and then it settles down to a single black hole which is present. And as a consequence, you see it emits a set of waves which propagates to infinity, and we actually detect them. Okay, good. And this is how the gravitational waves three phases work. We have a in-spiral phase to start with, then we have a merger phase, and finally we have a ring down phase. In-spiral means these two objects are moving around each other. Merger means these two objects in spiral, then they merge with each other, and that forms one single object which sort of moves, and then it settles to a single. The ring down can be thought of as if you have gone to temple, there must be this, this bell thing which you struck, and then there is a sound which comes out. Now the sound does not come out for a long time, it comes out for somewhat short time, and then the bell again comes back to its initial state. It's the same thing. There is some pattern structure which oscillates emitting gravitational wave. For the bell, it was sound, it is gravitational wave, and then it settles down to a definite state, another black hole. And this is something people have observed. I will show you another event where it was for the neutron star. I showed you two options, black hole or neutron star. So this is the corresponding wave from a neutron star. What happens when two neutron stars merge? So, oops. Okay, okay. Okay. So, what is going on? Now you can see. Okay. Yeah. So I guess you can see now. So this is exactly similar that you see a lot of electromagnetic emission from the system. The last thing, so I'm almost at the end of my talk, is about the shadow of a black hole. So this is about directly picturing how a black hole looks like and its surrounding looks like. So this is how you actually see a black hole. So effectively, it is not an effort of a single telescope, but rather an effort of a large number of telescopes worldwide, as you can see, so that it uses the whole Earth as a receiver of the signal which is being observed. And you know how much resolution this particular observation has? You can actually see a golf ball on the surface of a moon using this particular experiment. So I will show you without further ado how wonderful this setup is. So this is our Earth surface, and you can see all these telescopes. Now we'll move towards seeing what these telescopes will actually see the picture of a black hole. We're moving towards the night sky. And that's a constellation called M87. We are moving towards that. See that M87 galaxy, which is here, and we are going towards its center. So this is exactly what the scientists discovered a few years ago, that this is how the image of a black hole looks like. So that means that we now have a pretty good idea about the physics of a black hole. So therefore now is the correct time to go ahead and bridge the gap between general relativity and quantum field theory in order to obtain the theory of everything. So I believe that in the future generation or in the next 10, 20 years, there would be a huge growth in this field of gravitational physics and black hole research, because we are getting a huge information about this very exotic, very mind-blowing, and extremely compact object that exists in our universe in a numerous manner. So therefore, if we can understand them, we understand how gravity behaves in the strong field regime, and if we understand the strong field behavior and the weak field behaviors, we know how gravity behaves everywhere. And if we know that, then we hope to move forward and merge it with the quantum theory in order to obtain a quantum theory of gravity or a theory of everything. So with this, I will thank all everyone. Questions, comments, I will be more than happy to take them. So I will stop here. Thanks a lot.